I forgot my little clicker today, so I will be constrained to the podium area. But yeah, so as Ken mentioned, I just graduated, and I am just starting here working with Citrus and as a postdoc. So thank you, everyone, for the warm welcome. And hello to all the people and robots people out there. So the high-level problem that I've been working on and will hopefully continue to work on is active search and exploration for mobile robots. So I want to get robots to a point where they can actively move around and acquire information about uncertain environments, and to be able to change their parameters. So when I say active, I mean to adjust things like location, focal point, other sensor parameters, to localize things, gather information in an intelligent and efficient way. Of course, there's lots of reasons why we want to do that, from demining to surveillance to flaw detection, and even things like medical robotics, which I will kind of end with as my future intended work with automated palpation and searching for things actually inside the human body. So there's a lot of applications for autonomous search and exploration using robotic systems. And so how do we get robots to be able to move around, search, acquire information autonomously? What I have here is a basic, high-level, active, closed-loop active exploration algorithm. So 4 basic components where the main questions are, where's the interesting information for whatever you're looking for, and then how do you actually control your system to move around and gather that information? So 2 kind of separate sides. And those sides can be broken down further into these 4 main categories. These are all super broad categories and really application dependent, and I'll talk about some examples later. And again, in the future work, when I talk about some of the possible surgical robotics applications, how we might go about closing the loop like this. But the work that I'm coming in with, my thesis work, is mostly on this planning control action step. So assume we have some sort of expected information, some sort of density function. We want to be able to do something with that to collect further information. So this sort of one little chunk of this closed loop big picture idea. And before I get into the nuts and bolts, I want to point out that a lot of the history of control comes from applications like anti-aircraft, missile tracking, plant regulation, where what you're trying to do is get a robot or a system, maybe a plant, maybe a ship, to stabilize to a single point or to track a trajectory. And so a lot of the methods that we have as control engineers or roboticists are really pretty good at doing things like tracking to a point or following a trajectory. Now, there's also a lot of practical applications, and search and estimation is only one of them, where what you want to do is actually be able to respond to a distribution. So what I'm showing on the right is an animation of a swarm system that's moving around with sort of simple avoidance collision behavior, and you see that it splits around an obstacle. So using a control strategy that's tracking the mean or the expected value of that distribution, for example, it's pretty obviously just not going to do a very good job of maybe observing that swarm. So that is a distribution. Another example might be foraging. I know there's a few different groups within people and robots that are working on agriculture. Foraging type behavior might be important there, where you have a distribution of crops that you're trying to respond to. So something that's not well described by single points or maybe even targets or waypoints. And I'm going to mostly talk about that in terms of search and exploration, but just keep in mind that there are a lot of other applications, really anything that's described by statistics. And so what the goal is, again, is to be able to plan control strategies in response to reference distributions as opposed to reference points or reference trajectories. And so the way that I do this is using the principle of ergodicity to drive trajectory design. So ergodicity is not something that shows up a lot in control, so it's not something that we're used to thinking about as roboticists, maybe unless you're pretty heavily math-focused. But ergodicity basically gives you a way of comparing the time average statistics of a trajectory, so maybe the path that a sensor takes over time, to the spatial statistic of a distribution, where that, again, might be the distribution of crops, or it might be the likelihood of finding useful information over your search space. So ergodicity gives us a way of comparing those two sort of different ideas by looking at their statistics. So a more ergodic trajectory distributes time spent proportional to a distribution, where you get to define that distribution. In designing control strategies, it's helpful to be able to actually think about what the time average statistics for a trajectory means. It's maybe not that obvious. So on the left is a distribution plotted in gray. The level sets representing maybe something like likelihood of localizing a target over the workspace. And two example trajectories, one in orange, one in purple. On the right, on the top, is just a 3D projection of the same distribution shown on the left. And then the bottom is a time averaged representation of those two trajectories. So the orange one spends more time just in that lower left-hand corner. The purple one ends up having a time average distribution that looks quite a bit more like the distribution on top. And these are both obviously kind of smoothed out representations, and I will get to why that is in the next slide. But the goal here is to be able to design trajectories that have that characteristic. So trajectories that are closer in terms of their statistics, such as the purple one shown on the right. So to be able to do that, you need to have a norm on ergodicity. And basically, that's just a norm on the difference between two distributions. There are many different norms you could choose. The norm that I have been using is a weighted norm on the Fourier coefficients of both the time average distribution representing your trajectory and the spatial statistics. The nice thing about using these Fourier coefficients, A, is that as engineers, we're really good at doing anything Fourier, and B, that you get a norm, and therefore later on an objective function that is differentiable with respect to the trajectory. Turns out that is not that easy to come up with a norm that satisfies that property. And so now that we have a norm, we can formulate an objective function. Objective function then lets us do optimal control. And so the objective function that I've been using has one term, that's that distance from ergodicity, so we want to minimize that to get a more ergodic trajectory. And then the second term is the integrated control effort. And that partially makes the problem well posed. It's also a nice thing to have so that we get to decide how those two things are weighted and whether or not we have a very active, exploration-heavy trajectory or something a little bit more conservative. In my work, it's also been important that any solution is pretty general. So I want to be able to come up with ergodic trajectories that are also dynamically feasible for different types of systems. So that means you have an optimization problem where you have a nonlinear objective and you have a dynamic constraint. Further complicate, this particular objective function is also not a Boltzmann problem, which in optimal control, we like things to be Boltzmann problems, which means it's an integrated running cost. So it's not immediately obvious that you can use trajectory optimization techniques, but it turns out that the linearization of this objective function is a Boltzmann problem. And so that just means that you can, in a pretty straightforward manner, apply trajectory optimization techniques. So part of my earlier work in this area was just showing that and demonstrating that you can actually formulate and solve these problems for dynamic systems. So this animation here, the trajectories probably look kind of familiar. But what's being animated here is actually the trajectory optimization procedure. So you start with an initialization. This was a gradient-based trajectory optimization. So you start with the orange trajectory, which is your initial guess. And then as the optimization proceeds, you get more and more towards the ergodic purple trajectory. I like this particular animation because it makes it feel, to me, more like your classic gradient-based optimization problem where you see it kind of wiggle around the minimum. So I find it sort of comforting. But it also just illustrates that you get really a lot of improvement pretty quickly. So even with a couple of steps of this potentially expensive trajectory optimization method, you get quite a bit of improvement. So these, as I mentioned, want to be able to do this for dynamic systems. So these are 3 different examples, 3 different planar PDFs where we have different dynamics that are constraining what type of trajectories we get. So the size of the state space or even the control space is different between these three systems, but they're both over planar distributions. We get similarly ergodic trajectories, although they're qualitatively quite different looking. And this slide will flesh those points out a little bit more. But the point I want to make, too, is that because we're calculating trajectories responding to statistics, so everything is defined in terms of statistics. Your goal is defined by statistics. The type of problem that you can both pose and solve using ergodicity as your metric is really quite broad. So in this left-hand column, I am defining a uniform distribution. And then the trajectories you get out that are ergodic with respect to that distribution are uniform coverage type distributions. And similarly, for a less uniform distribution, you get biased coverage, bimodal PDF, and then even distributions that start to look a little bit more like maybe a traveling salesman problem, where you have these really sharp peaks localized or even a single target. All of those can still be described using statistics. And so you get kind of the span of these classic coverage type problems to more targeted problems, but they all can be described using statistics. And you get different qualitative types of coverage based on your dynamic constraints, but similar ergodicity across the different dynamics for the different types of distributions. Now you'll probably notice that the number is quite a bit higher on the right. And so this is the distance from ergodicity, so big is bad. That actually has to do with the dynamic constraint. So because your distribution is really sharply localized and you start not at it, there's actually a physical limit to how good you could ever do. So all of those were open loop trajectory design, where your distribution is not changing over time and you're responding to a time invariant distribution. Turns out you can also just add time as another dimension that you're calculating Fourier coefficients over, and you can come up with trajectories that open loop again. So you're not updating this PDF. This is just an estimate you have that is time evolving. You can track time evolving distributions as well. So these are two different examples of distributions you might be interested in. The top is a Monte Carlo simulation where you have some noisy dynamics and something's evolving. So your estimate of maybe a person running along is getting more and more diffuse as time evolves. And on the bottom, this is the simulation I showed before, where you have this swarm that's interacting with an obstacle and splitting. In both cases, the distribution is calculated based on a set of particles. So that's the grayscale thing that you see. And we can calculate trajectories that are ergodic with respect to that time-evolving distribution. Again, this is all open loop. So an example of when you might use it is if you're going to deploy a robot, tell it to do its thing for 10 hours, and then get it back and process all of the data. So this isn't a closed loop problem where we're collecting measurements, updating the PDF as it's evolving. Of course, for search or estimation, we do want to be able to do that. So everything I've been talking about has just been this little lower left-hand block where you're planning control algorithms based on a distribution. But we want to be able to start to fill in all of these different blocks for particular applications. So some previous work that I've done, I'm going to kind of use to explain what those pieces might look like. And those pieces are very application dependent as well. So one robotic application that I did in collaboration with Malcolm McIver's group at Northwestern was using this SensorPod robot, which is a bio-inspired robot based on a particular type of fish that lives in the Amazon River. And it's a pretty interesting fish because it hunts at night in very murky waters. It's basically blind. And it therefore has evolved a pretty interesting sensing modality. So it self-generates an electric field. And then the way that it actually gathers information about its environment to, for example, look for prey is by sensing objects that have different conductivity than the water. So this might be useful, for example, if you have a robot that's exploring in an oil spill where vision cameras are totally useless, but you might be able to use a sensor like this where all you need is conductivity. And robot is operated by a gantry system, and I'll skip a little bit of the detail there. But the basic objective here, and this is a video of the fish actually moving around exploring the spherical object, is to get that much clunkier robotic version of the fish, which has the same sensing modality, to be able to do something similar, to move around autonomously, explore an underwater environment, and localize a spherical target. And this animation here is the outcome of closing the loop around an ergodic trajectory optimization procedure using a measurement model and updating the probability as we go using the SensorPod robot. So we're trying to kind of emulate what the fish knows how to do using the same sensor model. And it happens to be a particularly nonlinear, unpleasant to deal with sensor model, where we have this lobe structure. And so as the SensorPod moves around for a particular object location indicated in black, you're going to collect different measurements based on how far you're away from the sensor model. So that gives you a way of predicting how useful future measurements will be, and that's going to ultimately drive the type of distributions that we want to be ergodic with respect to. Filling out the rest of this, again, for particular applications, different choices are going to make more or less sense. For the fish, a simple Bayes rule to update the location of your spherical target worked quite well. And then because we have that really nonlinear, non-unique sensor model, you need a way of taking your measurement model, taking your belief, translating that into then the robot workspace. So what is your expected measurement model, which is very nonlinear, and your belief, which might be in a totally different space from your state space. It might be radius or something like that. How does that translate into a map that you can respond to? So I've used Fisher information, and specifically the expectation of the Fisher information, related to entropy mutual information. And the expected Fisher information, again, gives you a way of taking what you know about your measurement model, your current belief, integrating that into a map over your workspace that tells you where the most useful measurements are most likely to be collected based on your current estimate and your characterization of the measurement model. This is a frame-by-frame shot of the animation that I already showed. But on the bottom, we have these ergodic trajectories where they're over a finite time horizon. And then on the middle row is the expected information density map. So it has that kind of strange four-lobe structure because of the nonlinear measurement model. And then the top is what we're trying to do, and that is your estimate converging. So I won't go into too much detail with this, but experimental results where we compared the ergodic trajectory to more simple, certainly less computationally intensive, maybe more obvious strategies like information maximization or gradient ascent. Those strategies tended to fail when you have other potentially distracting objects in the environment, or if you have multiple objects you're trying to sense. So anywhere where there's going to be local maxima in your search space, which is, for real systems, probably largely unavoidable. The fact that you get to explore enough using ergodic control is really important in terms of robustness. So this slide is illustrating, again, we couldn't do this on the actual robot. The robot is kinematically driven. But in simulation, plugging in different dynamics, you get different looking trajectories, but the evolution of your belief, which again is what you actually care about, is pretty similar no matter what. So that's something, again, that's a benefit of the trajectory optimization method that's used in combination with the ergodic objective function. Different sensor model, same idea. We want to use ergodic control, but we have a different representation of your expected measurement. But again, the same basic four-section closed-loop algorithm applies, where we have our belief, we have our information map, and we have our control algorithm. And in this case, we have a planar workspace and introduce distractor objects, which look similar to the target that we're trying to localize. So again, we're looking for a circular object in a planar area. And these distractor objects, because they look similar, they're going to give you measurements that are distracting. So they look quite a bit like your target object, but not exactly the same. And what that means is that you get local minima. So on the bottom are 3 examples of trajectories. These are 1D trajectories because only the orientation of the sensor is changed here. Uniform sleep on the left, which does converge to the correct target as long as you give it enough time, which isn't entirely surprising. And then information maximization, which gets stuck pretty easily on a local maxima caused by the distractor. And on the other hand, the ergodic control strategy, which looks quite a bit more expensive than the information maximization strategy, because it has all of that exploration that happens up front, is able to reject the disturbance caused by the local maxima from the distractor objects. And we can extend that to 2D, where you can really see the distractor object kind of causing a local maxima in a couple of these different areas. But because we get this exploration, which potentially at the cost of control expense, you get the right result. And that's what's important at the end of the day. So summarizing my past work, ERGODICITY gives you a way of encoding both exploration and exploitation. And by that, I mean when you have a uniform distribution, what you care about is coverage. You get coverage because you're responding to the statistics. On the other hand, if you happen to have a really tight estimate, you're going to get more targeted exploitation-heavy type behavior. So the trade-off doesn't actually happen. It's sort of implicit in how the problem is defined. By encoding this into a metric, so the ergodic metric, we can use optimal control and constrain the types of trajectories we get using potentially nonlinear dynamics. And closing the loop, I didn't talk about the actual experimental results too much, but closing the loop provides robustness with respect to things like disturbances, noise, uncertainty in your measurement model, because you're not overly converging, not exploitation heavy too early, because you're explicitly considering the statistics of your estimate. So moving forward, there's a couple of things that I'm going to be working on just in terms of the control strategies, the algorithms themselves. So since I've been doing a continuous trajectory optimization, that can be a little bit expensive. So coming up with faster approximate algorithms that we can do in real time is definitely something to focus on. Time horizon optimization, again, those are all open loop where the trajectories are calculated for a fixed time horizon. How long that time horizon should be is an open question, and I think also very problem dependent. Extension to non-deterministic dynamics. So we had calculating deterministic control strategies for these non-deterministic objectives, but there could be some interesting results where if you maybe can't guarantee that if you have non-deterministic dynamics that you can localize to a particular point, but you might be able to guarantee that you are ergodic with respect to a certain distribution depending on what those dynamics are. And then, of course, other applications. So I have a couple of different examples of particular sensing problems and sensing modalities I've looked at, but there are definitely many other applications that I could consider. And one of those applications that I'm going to be working here and that I'm very excited about working on is robotic surgery. So Ken's group has been doing a lot of work on all of these different parts of getting a DAVINCI robot to the point where it can localize tumors or arteries inside the body and then cut, debride, close up the wounds, mostly autonomously. And part of the reason we want to automate this is for something like palpation, the DAVINCI doesn't provide haptic feedback back to the surgeon. So automating that particular part is going to be really important. And so Ken's group, and particularly Stephen, have designed this really low-cost, small, cheap, disposable haptic probe that can actually be inserted and used to scan, for example, the liver, the kidney. And this is a video that they have created that shows this palpation in action. So this is just sort of a raster scan, but you're able to, using, again, this very, very cheap, low-cost, disposable sensor, get this pretty nice representation of the actual what's going on under the skin. So using a camera, you can figure that out. And again, because there's no haptic feedback using the DAVINCI robot, the surgeon isn't able to directly gather that information. So this is creating a map, but it's maybe a little bit slow, and it's all also open loop. So there's no way to actually refine this map right now. So I'm interested in combining my previous work in closed loop estimation with this particular sensing modality and this application. This diagram again. But there's a lot of open questions that make this problem pretty interesting. Some of them are with respect to the sensing model itself. So is deflection, which is what the actual measurements collected are those rich enough? Do we need something like velocity or lateral force as well? Or just by carefully controlling the robot, can we use that very simple sensor model to get all of the information that we need? Because it is deflection, we need an accurate surface model. So part of our group is going to be working on reconstructing a surface model and then ultimately improving that during the closed loop estimation procedure. Interesting question too is how do we parameterize inclusions? Is the right thing to do to actually formulate a map over the entire surface of interest and then try and compare that map to the actual information you want, which might be depth and shape? Or do we want to go ahead and try to actually learn the connection between depth and shape and this deflection measurement? Those are kind of two different ways of posing essentially the same problem, but they're pretty different in how you would actually solve it. And then how do we predict useful measurements and characterize uncertainty? So there's some interesting features of this sensor itself and of the problem that make this a little bit tricky too. And so that would be different from my past work, certainly. And then would ergodic search help in all situations here? And I think the benefit would really be tissue is not going to be uniform. So there's going to be lots of non-homogeneous regions that might cause perturbations in the sensor. And so while that image that we showed looked pretty easy and like you could use maybe sort of naive algorithms to localize, in real tissue where you might have different regions, you might have arteries, you might have bone, having an algorithm that's appropriately careful and robust to those type of disturbances is going to be really important. So that is future work, sort of other work they have done as well to characterize the sensor. And this is some more of Stephen's work as well. So this would be more on the lines of how you actually would go about parameterizing the problem. So if you have something like a CT scan, you could say, OK, now I have maybe 6 parameters I want to solve, which is the orientation and the depth of those 3 images. Whereas if you don't have a CT scan, you might want to do something more like the mapping approach. And so that's all I've got for now. Do you have any questions?
Excellent. Do you want to say a little more about maybe the issue of computation? Because right now, you do it offline, right? You do the computation, and you mentioned that it was a little bit.
Yeah.
That you mentioned it was a little slow, and so can you say a little more about how that might work in an online scenario where you have to recompute?
So, depending on what you could do is do sort of a greedy control strategy in the ergodic space where you're just calculating the next best location you want to move to that's going to minimize that ergodicity. Over a time horizon, that won't necessarily be the shortest path than if you did the full trajectory optimization, but calculation-wise, it would be much faster. Also, just optimizing your code and maybe doing a 1-second time horizon, it's going to shorten the amount of computation it requires. Most of those trajectories I was showing was about 10 seconds, and they would take maybe 30 seconds to compute.
Mm-hmm. Okay. Good. Jeff? Back.
Hey, so it looks like you use like expected information density. I'm just curious how important is that to like the ergodicity? Like, is it important to be able to solve the problem, or if you had something else that sort of managed exploration exploitation, could you like plug that in instead of that?
Yeah. So those components really are separate, in that all you need is a distribution. So that distribution could just be if you have a map, if you have an occupancy grid, and you have a representation of the uncertainty. That could be what you perform ergodicity with respect to. Okay.
So is expected information like, does it have benefits in terms of computation? I'm just curious.
No, it's probably, it's one of the more computationally expensive parts,
okay.
Yeah, because you're taking some integrals and some expectations.
Yeah.
Depending on your problem. For the fish robot, it was very important because the sensor model was so nonlinear that if you, for example, just go right to where your expectation is maximized, so the location of the target, your measurements are not at all informative just because of what the sensor looks like, how the sensor responds. Whereas where you really want to be is just kind of offset a little bit from where the target is. That doesn't always matter. If you have a nice linear sensor model, you could probably just use your belief directly.
Interesting.
It also kind of relates to the element of priors, because like when you had the CAT scan, as you said, you might just be trying to optimize now your six vector of the position orientation of where you are with respect to that. That's actually kind of an interesting variant.
Or if you know that it's well modeled by an ellipsoid, then all of a sudden you just have maybe 3 parameters you need to optimize.
Good. Stefano, you had a question too?
Yeah. I work a lot in this area, maybe even too much. I don't have lots of questions, but I have
Wait, I'm going to give you the mic.
So when you're dealing with a real search problem, the one that is going to ask you to find something typically is interested in 2 parameters, which is how long will it take, and can you give me a guarantee of the error on the mission. So if I tell you to find something, can you give me an answer within X minutes, seconds, whatever, and could you guarantee that your correct answer, that your answer is correct with a certain probability? Because very often we eventually miss to find the target, or we pinpoint it in the wrong location. That's going to be relevant for cancer, palpation, for searching down aircraft and whatnot. So I wonder if this framework, which seems extremely interesting, can be related to these 2 parameters.
Yeah, I think that's sort of a pretty deep question, because what
I know.
Excellent question. But I mean, so what you're doing is mapping the statistics, right? So how good your search strategy is directly related to how good your estimate is. So if you have a really noisy sensor, or it really is just a very bad environment, you won't falsely converge. Does that make sense?
If I have a very bad sensor, I may be asking for more time.
Right. But those are almost application dependent. Yeah, I don't know. I'd have to think about that. I mean, I don't... Yeah, that would almost be more in the belief update space, I would say. Yeah. I certainly don't have a good answer for you just from the control side, whether or not you can guarantee.
So that is a very relevant question.
Yeah.
Comes up all the time.
Right. Yeah. At the same time, you certainly don't want to say you can guarantee and then guarantee to the wrong thing, or converge to the wrong thing.